All right, we're going to start from the very basic, which is the rate of change, which you should know already. Now, rate of change, what do you think it is?
Gradient.
Gradient, thank you very much. What we need to think about is gradient in terms of not just a straight line, all right, a curve. So here I'm going to get you all to recall what a function is. You must be able to actually recall the features of a function like roots, y-intercepts, stationary points, points of inflection, local maxima, local minima, and global maxima, that sort of stuff. You should be able to define the gradient of a function as a slope of the tangent at any given point. Describe functions as increasing or decreasing between given interval, and sketch graphs given certain conditions. All right? So it's basically a revision lesson on function. Now, think about a function. It's a mapping of two sets, i.e. a domain x to a range y, such that every x value has one corresponding y value, 1 to 1, or multiple x values have one corresponding y value, many to 1. So you've got 1-to-1 function, which is linear, and many to 1 function, a quadratic. All right, 2x can produce many to 1. So the 2x, the x here, when x equals to, let's say, for example, this one x equals to 1.5, it produces this. X equals to minus about 3.8, it produces that. So you know that there are two x's to one y value. All right. So there is many to one relation. This is 1-to-1 relation. So think about what a function is. So it's a 1-to-1 relation or many-to-one relation. All right. Now let's have a look at the first one. How do we describe certain things? Things like x-intercept, y-intercept, extrema, and concavity, points of inflection, and behavior. All right. So I'm going to use points. Let's use points A, B, C, D to actually indicate x-intercept or the roots. You know that it will be point here. If this is working. Yep. So the point will be one point here, here, and here. Let's call these 3 points A, B, and C, the roots. Just indicating on your graph, please. Y-intercept, of course you know what this point is, which is, let's call it D. All right, can you think about what is local minima and what is local maxima? All right, local. And what is global? So if you think about local, let's start off with maxima. This looks like a maximum, right? Yeah? And, however, this only applies to just that little bit. That's a local maximum because that is the peak, and when you go up, it will come down. All right? Whereas there is actually a global maximum where there is no end to it. You can go on and on and on and on. Right? So here, this point here, let's name it 3. Let's call it a local maxima. Whereas global maximum, it goes on. It doesn't finish. It's plus infinity. Local minima, again, it restricts to this point, this bit. And that you can see, although it's a minimum, but that's only locally existing around this area. And this one, it goes all the way down. So that is negative infinity, E, and let's say this is F. All right. Now, do you think there's any other global maxima and any other global minima? Not global, sorry, local. What do you think? What about this area here? Don't you think that it peaks a little bit and then come back down and trough and go back out again? Yeah. So that should be a local maxima somewhere here and a local minima somewhere here. Looking at this graph, without really going into doing any derivatives, I will say that looking at this graph, that point is a local maxima, that point is local minima. Agree?
Why is that?
Because it's going up and then there's a change of gradient and then going down and then change of gradient going up.
Then there's another local maximum.
Yeah, that's a, and yeah, the point of inflection is somewhere around here. So let's start about thinking about it there first. So that point would be another, let's call it G, global maxima. And this point is H. Alright? So you do have, you got to look at the graph. So that point and that point, you're just estimating at this stage. You cannot tell. Unless you know the exact coordinates, you know the equation and stuff like that. You really can't tell. But looking at that, yeah, I will estimate G and H. One is a global maxima, one is a global minima. So concavity, what do I mean by concavity? Which one is concave down, which one is concave up? So think about that. Is that concave up or concave down? Hmm? What does it look like? Concave up or concave down? What is that? Concave up or concave down?
Down.
That's down, that's up. Right? Agree? Yeah? Concave down. So I've got concavity, this is concave down. This is concave up.
Yeah, there's the ending.
Now, any other point which will have concave down and concave up?
Yes.
Here, what about here?
Yes.
Yep, somewhere around here. Concave up. Somewhere around here is concave down. Right? So you do have concave up, concave down. Concavity. The point of inflection is when you change from concave up to concave down. Alright? So somewhere around here, sort of right in the midpoint, that would be, let's say, F, G, H. Let's call it J. Alright? And from here to here, down to up, somewhere around here. Okay. So from here to here, maybe I would say D could be the point of inflection. It might be somewhere around here. So I'm guessing it could be just sort of a midpoint around here. Just guessing. Alright? Without, like I said, without really knowing the exact equation, without really knowing the derivative, I can't tell. I can just guess. So I got J, K, and let's call this point L. J. Oh, sorry, not that. That would be not here. That would be J, K, and L. Alright? So you can see these are the points, those are the important points for you. Point of inflection, changing from concave down to concave up. And finally, the behavior. As x approaches infinity, what happens? Y approaches. X approaches infinity, y approaches negative infinity. And as x approaches negative infinity, y approaches positive infinity. Alright? So you do know, you should know the critical feature of a function. Now, rate of change. The rate of change of a function defines how the dependent variable, which is y or fx, is changing with respect to change in the independent variable, which is x. So if you're not sure about the definition, I'll suggest you write this down, please. Rate of change of a function defines how the dependent variable, how it is changing with respect to a change in the dependent variable, which is x. Independent variable, which is x. So yes, you're right. Rate of change is the gradient y over x. All right. Now we'll take it a little bit further. Can I move on? Yeah. Not yet. All right. I'll move. give you a couple more seconds, then I'll move on. All right, moving on to the next one.
Oh, yeah.
All right, here, if you look at the first graph, the graph on the left, a straight line, there's a constant rate of change. Correct? Y over x doesn't change at all. The gradient is constant, correct? Do you agree?
Yeah.
Whereas for the second graph, what would happen is, you know that the gradient changes from negative to positive. Agree? So here, the gradient is negative. Here, the gradient is positive. Right? Now, how do we determine the gradient?
Calculus.
Yeah, calculus, but before that, what do we do?
Draw a line.
All right. Yes, draw a line.
Tangent line.
Thank you. So, from our knowledge of linear functions, we define the rate of change as the gradient of the function, right? So, how do we measure the gradient of a non-linear line? So, it is a tangent if we draw a line. So, graphical interpretation of a gradient. The gradient of a non-linear function, that is a function with the rate of change, with a changing rate of change. The word changing is important. So, highlight that. The changing rate of change can be measured at any point on the graph. So let me highlight that information. So what you are thinking of, the gradient is changing all the time. The rate of change is changing all the time. So to find the gradient at that point, or the rate of change at that point, you must consider the tangent to the curve, which is the line that just touches the curve, that's all. So here, if you want to find the tangent here, you need to draw a line that touches the curve here. This point, you draw a line that touches the curve. What happened? Once you draw a line that touches the curve, what is this telling you? Can you find the gradient?
Yeah.
With 2 points, you should be able to find the gradient. Correct?
Yeah.
Okay. All right. Move on to the next one. Next slide. Let's describe the critical feature in terms of the gradient. This time, I want you to think about gradient. Think about the gradient only. So you need to think about stationary point. The definition of a stationary point, write that down please. Definition of a stationary point is a point on the curve where the gradient is 0. Alright? So any point on the curve where the gradient is 0 is called a stationary point. Alright? Generally, the turning point, the local maxima and the local minima. I will show you the horizontal points of inflection in a few minutes. Horizontal point of inflection is when the gradient is 0. At this stage, I don't see in this graph any horizontal point of inflection. So here, turning point, local maxima and local minima, let's call it A and B. A and B. So that is actually the turning point. The gradient here is 0, the gradient here is 0. Because when you draw the line tangent to it, it's a horizontal line. Draw a tangent to it, it's a horizontal line. Alright? Now, horizontal point of inflection is when you have a situation like you've got, let me do a different curve, y equals x cubed. Alright? So y equals x cubed, it looks something like this. Correct? So this is y equals x cubed. Alright? This point here at 0, 0 is called the horizontal point of inflection because the gradient, when you draw it, obviously I didn't draw it that well, but if you draw it, that is horizontal. So the change, the horizontal point of inflection means that point over there, and that is a stationary point. Alright? Horizontal point of inflection. In fact, in this straight line, there is no horizontal point of inflection. It's something like y equals x cubed. You do get a horizontal point of inflection. Right. So let me write that down. horizontal point of inflection. All right? Now, what is the point of inflection?
Where the gradient changes.
Where the gradient changes. So you got to think about what do you think about the increasing interval? And what do you think about the decreasing interval? Where would the increasing interval be? Where does the gradient increase?
On the right side.
So here, from this point to somewhere around here, it increases, correct?
Yeah.
This point to somewhere around here increases. The rest, all right? So if I label two other, actually, turning point, local maxima, that's another one, and minima. I should have realized that as well. Spoke to you about it just now, but I did not draw that. So let's say call this C and D. C and D. All right? So you can see that between A and C, that's increasing. The interval between A and C, D and B. Increasing interval AC, DB. All right? Decreasing from here onwards. That's decreasing. Yeah? And here, C and D. And from B to X infinity, that is decreasing. All right? So A, that way, and B, that way. Those interval greater than B, less than A, greater than B. Those are all decreasing interval. So you must be able to describe the critical feature in terms of a gradient.
Wait, so why is A decreasing?
A decreasing less than A. Anything is decreasing. What's the gradient? It's talking about gradient, negative gradient now.
Yeah.
Talking about gradient now.
Yeah.
So negative gradient is decreasing, positive gradient is increasing.
Yeah, okay. Yeah.
All right? Now, let's have a look at example. So describe the gradient of the graph fx equals to x to the power of 3 from its graph below. So what you can say that is increasing, keep on increasing, and then increasing until you get the plateau here, which is where the gradient is 0, horizontal point of inflection, and it's increasing all the time. Right? You can see that's increasing, and then slowly slowing down. All right, and then 0, the gradient is 0, and then increasing. All right. So here, this point, gradient equals to 0. This is increasing, and that's increasing. Right? So now, can you use this graph to determine the gradient of x? Fx equals to x cubed when x equals to 2. How would you do this? When you draw a tangent, how do you find the gradient of this tangent?
Identify 2 points.
Find 2 points. What 2 points will you use? What 2 points will you use?
2, 8, and like
What 2 points will you use?
4, 20.
Look at this. So here, there's quite a defined point, right?
Oh.
Yeah? So that's somewhere around here,
2 and 320, right?
Yeah.
that point, yeah? Which is 3, and that's 20. And then going down here, that's another one. That's a good one to use. 1 and minus 4. So you can work out the gradient. So the gradient of that point will be, gradient will then be 20 minus 4 divided by 3 minus 1, which is 24 divided by 2, which is 12. That's a gradient. You can use a tangent line to do that. All right? Now, there is an easy way of doing it if you know the derivative, but let's not do that yet. We're just going to do the introduction, that's all, which is the introduction to rate of change. Example 1. Happy with it? Yeah? I mean, if I don't have that, I can tell you straight away it's actually 12, if you know your calculus. Now, Here, you're asked to sketch a possible function that satisfies the following condition. Fx equals to 0, at x equals to minus 2, and x equals to 3. The gradient is 0, stationary point, and whatever. At x equals to minus 4, 1, and 5. The function is increasing between minus 4 and 1. Elsewhere is decreasing, or 0 as defined above. The local maxima occurs when fx equals to 16. Alright, now, let's think about what information we have.
You have the x-intercept.
Alright, you know the x-intercept. Fx equals to 0 when x equals to minus 2. So what I would do is, I would actually draw a couple of lines. Here is minus 2. Let's say this is minus 2. And this is x equals to 3. Alright? And we also know that stationary point occurs at x minus 4. X is minus 4. Oops, let's change this point. Let's call this x is 1, x is 3, and x is 5. Right? So from there, let me do some dotted line. Just dotted line. So we know exactly where the points are. When you're asked to draw or sketch, this is always a good technique to use. Have some dotted lines so you know where things are. And use the ruler, please. Alright. Now, we've got those 5 dotted lines. We know that fx equals to 0 and x equals to minus 2 and x equals to 3. So starting off with this information, fx equals to 0, x minus 2, and x equals to 3. I've already got 2 points. The gradient is 0, stationary point at x minus 4. So you know here there's a stationary point, here there's a stationary point, and there's a stationary point. Alright? The function is increasing for minus x, minus 4, x between minus 4 and 1. So you know that's increasing. Right?
Wait, so
But the rest, yep.
how is it maximum at 16 where it's only increasing?
It's just given it to you, that's all. The maximum, the local maximum occurs when fx equals to 16. That's given to you.
But it says elsewhere it's decreasing.
Yep. So what happened is, you will see that from here to here, it's increasing,
Yeah.
and then somewhere here it will come down,
Yeah.
because that's a point of inflection.
So
That-
that'll
that's
be the local
that's the maximum.
Yeah,
That is that will be your local maximum
at 1.
at 116. So there,
Oh,
that
okay.
information there, if you go increase, and then here the gradient is 0 there, that's
Yeah.
coming down.
I thought
All right.
it's just x.
So let's label this point as 116. And then you know this is going up there. Alright, we don't know the y-intercept, whatever. Doesn't matter. And then elsewhere is decreasing. So you know that this one will be going up that way.
Minus 2 is the x-intercept.
Hang on. I've got to go. Whoops. My fault. Thank you. I need to go through the minus 2, don't I?
Yeah.
Ah,
Just go under.
thank you. So I need to do that. My fault. I totally forgotten about that. Got a bit excited. So here there's 1 minus 16. And then it has to go through here. Positive. Alright, come down. And then here it will be something like this.
Isn't that not elsewhere as decreasing then?
Sorry?
Because that's. Okay, yeah.
That's a gradient,
It's still
decreasing gradient.
decreasing. Yeah,
So
but
that's
then. Yeah.
positive, 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 positive until 0.
Yeah.
And then
But
I'm
then,
going
but then there's another turning point.
yeah. Hold on. So we are going down, we are coming through here, correct?
Yeah.
And then there's another, it says here, that is
that will be
stationary point.
Yeah.
So it will be
Increasing from.
horizontal point of inflection. So if it is horizontal, that point there.
Oh.
Yeah, it has to be case.
Got it? So it's still decreasing except that point where the gradient is
Yeah,
0.
oh my god, that's so smart.
So you got to think about all the information given to you. This is how you sketch.
So
I mean,
more questions like this because I completely failed. Like instead of this.
I've seen questions like this in the exam, except for practice. That's all right.
Yes. But there's another one on the left.
There's another one on the left. So that is this point here. We don't know how far down is or how far up there. That's one point here. So that is the turning point. The gradient is 0 here. Gradient is 0 here.
The x-intercept. It says
You don't know.
Minus 2 and 3. That's it. We don't know that one. We don't know that one. That's fine. We don't know, but we're going to assume that that's another point. You're given 2 points only. You're given 2 points only. But the third point, yes, you cannot. It's increasing. It has to go through the x-axis, correct? It doesn't say that it stops at x-axis, so it has to go through the x-axis. But we do not know what this point is. These are the 2 points are given. We know the gradient here, gradient here, and gradient here. That's all. Yeah? Happy with that? All right. I'm going to stop here. You got plenty of time to do your some exercises. So this is start of calculus, and I really do want all of you to think about my T-shirt here. All right?